Good afternoon, folks. I'm Tong from ByteDance. I'm very happy to present our paper here. In this paper, we look at the multi-party conferencing scenario, and different from the other papers in this session. And our proposal, AsTree, focuses on the audio subscription problem. And normally, I should have explained how important the problem is, but I believe you have probably heard that many times, so I'll just not ramble on that too much. And before getting into the topic, just please allow me to first introduce ourselves. We're the Volcano Engine RTC team, and we support various RTC applications, including our own apps at ByteDance, as well as many others from our customers. And Lark, with its online conferencing service, is the focus of this paper. And with our new architecture, AsTree, we have managed to support more than 1,000 participants per room for our customers. And this is the outline of my talk. I'll explain the motivation, design, and performance of AsTree, and also for your convenience of understanding, I'll start with a short brief of the currently dominating multi-party conferencing architecture, which is based on selective forwarding units, or SFUs for short. And today, a majority of service providers, including us, choose to build the conferencing system based on SFUs. And it is the dominating choice because of its cost effectiveness on the server side. Like the illustrating figure shows here, the SFU media servers only forward audio and video streams without decoding them. And also, SFUs are distributed on the edge and cascade with each other to connect participants from all over the world. That is the basic idea of the SFU-based architecture. And in the process of scaling to larger and larger conferences, we find serious scalability issues of audio subscription. And the first problem, as shown here, is the signaling storm. And unlike face-to-face talking, before an audio stream can be forwarded from its publisher to other subscribers, the publisher should first broadcast the published message. And each publisher will generate ON signaling messages, which combines to ON squared for each conference room. You may wonder why this is not a problem for video conferencing, and that is because there we could aggregate the published signaling of multiple video streams so that we can lower the frequency of signaling broadcast. Unfortunately, that is not suitable for audio subscription because audio usually has tighter latency and timeliness requirements, and we do not want to wait for the aggregation. And the second issue is the indefinite resource overheads induced by audio streams. And for video, the user interface naturally induces an upper bound for the number of video streams a single participant can subscribe to. But for audio, valid audio signal may come from anyone. And for simplicity, in our previous implementation, we enforce a straightforward subscribe to all strategy. And each participant subscribes to audio streams from all the others, including those who mute their microphone. And such subscriptions are initiated right after every participant joins the conference, so that when you want to speak in the conference, you don't need to wait for the publish and subscribe signaling interaction to finish. You just click the unmute button and start talking right away. But as the trade-off, the client-side resource consumption increases linearly with the room size. And on the server side, we suffer from ON squared overheads again. And the last issue I want to bring up here is the mesh cascading between SFU media servers. The full audio subscription between each pair of participants requires us to build an overlay mesh between the SFUs involved in each conference. And that is particularly a headache when a new participant joins an ongoing conference and connects to a new SFU. And we really don't like the resulting high complexity to update and maintain such cascading topology. And to illustrate the influence of the scalability issues intuitively, here I provide an example comparing full lot, which is our previous implementation, with AsTree. And the experiment is conducted in our test environment, where we can initiate any controlled number of virtual participants and connect them to a single SFU. we can see that due to signaling storm, full load induces an apparent CPU peak on the SFU in the start of the conference. That is when many participants join together in bursts. What is worse, the CPU usage of a 1,000 AsTree room, a 1,000 participant AsTree room is only slightly higher than that of a 125 participant room under full load. And that means the full audio subscription significantly restricts our server capacity. So we're strongly motivated to improve that for a better cost effectiveness. And the core idea of AsTree is pretty easy to understand. That is, at each time point during the conference, critical audio information only comes from a few loudest speakers. Therefore, an ideal realization would only select a small number of audio streams, regardless of the room size. And the high-level architecture of AsTree has no big difference from the existing popular design. We keep the division of user plane, media plane, and control plane. And the user and media planes are divided into geographical regions, and participants are directed to their nearby servers. And for each conference room, we calculate a cascading tree at the control plane using the connected participant distribution and inter-server latency. And then SFUs are cascaded accordingly. But note that this is only for audio subscription. The routing and cascading for video streams are not changed and remains independent. And if we look at the topology of a cascading tree, there are these two hierarchies. First, within each region, we select one SFU server as the region delegate. And all media servers within the same region cascade to the region delegates. And similar to that, we select one of the region delegates as the master delegate. And the master delegate cascades to the other region delegates so that they form a spanning tree among all involved regions. Now, I'll explain how we select the delegate servers using this example. For intra-region delegates, we just use the first SFU involved in each region. Like here, the top left SFU is the delegate of region 1. And the second SFU involved in region 1 should cascade to the first delegate SFU. And it is the same for region 2. First SFU there is the region delegate. And at this time, since there are only 2 regions, the only inter-region cascading option is to cascade the 2 delegate servers. And we do not need to select the master delegate until when the 3rd region joins the conference room. And our current implementation will try not to tear down already established cascading links. So in this case, we need to cascade the delegate SFU of region 3 to either delegate of region 1 or that of region 2. And either one of the existing 2 delegate servers will be selected as the master delegate. And that process uses an objective of minimize longest cascading path RTT. I'll explain that in the following slide. Now, in this example, assume the delegate of region 2 is selected as the master delegate, and we cascade the delegate SFU in region 3 to it. Note that the master delegate itself is still the delegate of its region. So when there are more SFUs involved in region 2, they will still cascade to it. And next, when participants gradually leave the conference, we may need to remove some SFUs from the cascading tree. While doing that, we only remove an SFU if there are no participants below its hierarchy in the AsTree topology. And the simplest scenario is when all participants are disconnected from a leaf node in the tree. In that case, we can safely tear down the intra-region cascading paths from those leaf node SFUs to their region delegates without impacting other participants in the same room. But things are different when it comes to delegate servers. For example, when the participant directly connected to the region delegate of region 1 leaves, we need to keep the delegates in the cascading topology because there is another participant in region 1. And similarly, we keep the cascading paths from the master delegates even after all participants in region 2 have left. And then when the last participant in region 1 leaves the conference, we can remove all SFUs in region 1 and region 2 together. And the last SFU involved in this room will be released when the conference is ended. Okay, next I'll talk about master delegate election. Theoretically, selecting a master delegate among a set of given region delegates is a spanning tree problem. And as I just mentioned in previous slide, we adopt the objective of minimizing longest cascading path RTT. Here's an example. Assume a conference involves these 4 regions globally. And there are 4 possible options for the master delegates. For each option, the RTT of the longest inter-region cascading path is shown below. Apparently, 299 milliseconds is the minimum one, so that ideally, we will select the SFU in West US as the master delegate in this example. However, I must point out that, remember, the construction and destruction of our AsTree topology is an incremental process, and we try not to change the already established cascading paths, so that we cannot always guarantee the optimality of the actual AsTree topology. But that simplifies our implementation, and at this moment, it satisfies user requirements pretty well. And based on the AsTree cascading topology, we conduct audio selection to reduce the number of audio streams to forward. And each SFU selects only a limited number of audio streams based on their average audio levels. And the range of selection includes the audio streams published by those directly connected participants and the cascaded ones from neighboring SFUs. And when forwarding the selected audio streams, an SFU will never send a stream back to where it is received. Like here, stream 1 and stream 3 are selected, and stream 3 will not be forwarded again to its publisher participant. And our dominant speaker identification algorithm has more details, such as how to avoid frequent changes of the selected speakers, and you can refer to our paper for that. And due to limited time, I also omit many other details, such as our implementation of the proactive audio stream subscription and our fault tolerance mechanism. Again, please read our paper if you're interested. And for evaluation, in addition to practical deployment, we conducted comprehensive benchmark experiments in our test environments and compare AsTree with our previous solution, Full-Lot. And some highlights are listed here. I want to strengthen that besides the significant reduced resource overheads, AsTree also optimizes audio and video rebuffering, especially for large-scale conference rooms. And that is because a fewer number of audio streams to forward also mitigates the congestion within the network. And in the production environment, about half a year after the deployment of AsTree, the median audio and video rebuffering ratios are decreased by 30% and 50% respectively. The improved user experience is also reflected in higher user satisfaction. And as shown here, we observe a 40% reduction in the ratio of negative user reviews. All right, to wrap up, AsTree builds a cascading tree topology to forward audio streams, and it only selects dominant speakers instead of enforcing full audio subscription. Our deployment experiences show that it improves the scalability of large-scale multi-party conferencing. Of course, there's still room for further optimization, like we may require more sophisticated problem formulation and more flexible cascading topology deformation mechanism to achieve even tighter latency requirements. And that is all from my presentation. I'd be glad to take questions.